Hey guys, welcome to another lesson of Bowas Academy. Today we're talking about like machine learning and neural network and stuff like that. So yeah, let's get this done. Anyways, okay. So first off, we need to establish some like wordology stuff and stuff like that. So, what in the Fortnite is AI? AI is artificial intelligence. What in the Fortnite is artificial intelligence? Artificial intelligence is intelligence that is artificial. So, but then, okay, so we did branch off into two different sectors. First, what the fuck is what? Sorry, my bad. What in the Fortnite is an artificial? An artificial means that it's like we're trying to replicate what the thing is. You know, it's not we don't have the thing, or maybe we do have the thing, but we still don't. But we still want to like replicate it for whatever ball reason, right? And stuff like that. So now the question is, we have the artificial down. So now all we need to do is get down the intelligence, right? But what in the Fortnite is an intelligence? And we have to realize something. Intelligence is like the ability to make proper decisions and stuff like that. But now you're wondering, oh my god, Bowas, what in the Fortnite is a proper decision? And to that answer, and to that question, a proper decision is being able to decide whether or not something is a tree. To be more specific with that, it's being able to like decide, being able to make a proper decision is like being able to, wait a second, there we go. So like for decision-making tasks, right? So whenever we're deciding stuff, right, there's stuff that's like objectively correct, such as like a big math equation, like the one that you can see here, which is going to be hold on, give me a second. Okay, it'll be 103 unvictillion, 438 vigintillion, 379 novemdecillion, 442 octodecillion, 745 septendecillion, 976 decillion, 639 quindecillion, 585 quadrodecillion. Wait, which section am I at? 895 tredecillion, 640 duodecillion, 975 undecillion, 465 decillion, 407 nonillion, 564 octillion, 872 septillion, 564 sextillion, trillion, 57 quintillion, 846 quadrillion, 485 trillion, 640 billion, 754 billion, 367,548 times 38 septendecillion, 499 sextecillion, 897 quindecillion, 541 quadrodecillion, 809 tredecillion, 715 duodecillion, 897 undecillion, 531 decillion, 537 nonillion, 890 octillion, 153 septillion, 980 sextillion, 853 quintillion, 101 quadrillion, 750 trillion, 953 billion, 850 million, 897,519, which results in 3.982160137452951 times 10 to the 123 power. So computers can do that. But what about subjective things like what's a tree? How the fuck do we define what a tree is? And every single decision has its background elements to like a situation that contribute to that decision. So, I mean, let's think about the fucking aspects of a tree, right? So we're thinking about a tree. Like, how big is a tree? Like, what the fuck is the shape? What's the shape of the tree? What are its leaves? What are its branches? What are its roots? What covers its body? Like, is it like what the fuck's its body? What's its color? Body color? What the fuck is body shape and stuff like that? You know, we have these preconceived notions, but the question is, we don't have fucking boundaries on what the tree is, right? So it's like, so you have to think about it like this. So we have all these things, right, of what a tree is, but we don't actually know what the boundary is between a tree and some other thing, right? So what's the difference between, say, a tree or air we need to make sure that we have some sort of boundaries based off those individual elements, and we can make certain boundaries. Well, we don't know what those boundaries are, but maybe we can combine those elements of what it makes a tree, or go beyond that, right? And so, what can we do? Stuff like that. And this is where I get fucking lazy and go back to this fucking Google document to talk about it. So, there's a couple of things. We can do about it. And they each tie to the idea of weighting certain elements of the thing. So, for example, okay, wait, this recording sucks. I'm gonna redo it. Teehee. So this is a good example right here. Suppose that you're trying to read a number from somebody's handwriting, right? So in the way we can do that is, what are some of the elements of a specific number, right? Well, in some cases, right, we can see that if we're just differentiating, let's do 1 and 5 for simplicity's sake, right? Well, what are the attributes of 1 and 5, right? Well, we can say that 1 versus 5, right? One has significantly more synergies. One big difference is symmetry, right? One is a lot more symmetrical than 5. What else? Well, 5 takes up more slots. Tends to take up more slots because 5 while 1 is just boom, gadoink, right down the middle, right? 5 is more, you need to go this way, and then down, then you gotta circle all the way back and stuff like that. That's very big. So we can say that that's intensity, right? How many pixels are being taken up? 5 takes up more pixels than 1. And for the sake of, and there's probably also other things, like for example, maybe we can say strokes, right? How many strokes does it take to for 5 other than 1? Or we could do something like find the precise precise straight length of it. So we need to have initially like the top bar, right? Has to be like generally horizontal. And then we need to have a slight bar, so like down me like a gap in between these places right here, right? And then we also have to have a sort of circular motion, where we would have to plot some sort of like a circular graph based off of that and stuff like that. So yeah. But for the sake of simplicity, let's just go for these two right here, and we have two main elements that we can start making our decision based off our grand decision based off of it. So we have our symmetry and intensity, right? Okay, cool. So how do we weigh these things to make a judgment on them, right? We don't know how to weigh these things to say, hey, these things in the blue, right? These things are like 5s, or these things in the red, they're supposed to be 1, right? How do we tell, like, well, we have our training data right here in the blues, so we can say, we can just make our, this is what the learning part of machine learning comes from, right? So we have our test data set right here, where it says, okay, we have our weights set to, like, whatever at this point, right? But we can change those weights to the point where based off the intensity and symmetry, based off of whether or not you get it right or wrong, right? So let's say that you have something with a lot of symmetry but very little intensity, right? And you guess, I don't know, it's a 5, right? And then you get it wrong. Well, you would change your weights to account for the one in that case, right? Because you got it wrong, dumbass. And so as a result of doing that repetition, right, of changing the weight slightly to base off of it, you are in a better spot, right? You're accounting, You're accounting for more as you do things, which is great. Awesome, cool. Now the question of the day is simple. Okay, so we have like, we're trying to estimate instead of our boundary. Wait. Let's go. Let me flip here. Um, the boundary line is something that is estimated, not something that can 100% exist. Whew. The boundary line is something that can be estimated, not something that 100% exists. We do not know. It is impossible for this to get a 100% precise boundary line on these things, because everybody can draw a 1 in a 5 difference. But that boundary line can change after training data is applied, where alterations are made based off of incorrect guesses. So we just change the weights and stuff like that, and that's how we get this initial line right here. Now, some people who are perceptronic, who are perceptive, might say, okay, but Bowas, this is a fucking line. You still have some things in the sample that is not accounted for. Can't you do something like have a specific line that comes through and just goes ning 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 ning, and what's it called? Like weaves through these X's? And you know what? That's a fair point. You know, if we had a way more complex line, we would be able to like have a better fit for the in-sample data. But this is where the more important thing comes in. The training data is not the same as the real world data. What is this concept called? Well, I'm gonna have to I'll probably have to make another slideshow. Oh no, but yeah. So we have 2 Fortnite backpacks right here, right? We can obviously tell that these are 2 Fortnite backpacks based off the Fortnite sticker off of them. But even if that didn't exist, we could probably infer that this is like the Fortnite, those little bear heads that like Fortnite came from and stuff like that. And we can also infer that these are the camo here is actually a bunch of people doing like their Fortnite dances, and that like silhouette dance style is kind of signature to Fortnite. But the issue is that if we focus our training data and our judgment on all these elements of like this pink backpack, right? So let's think about it like the bright colors, and then the animal face, and then what else? Maybe like the animal face, the pink, the like bold colors and stuff like that, and a small tag. We would be focusing way too much on all these elements instead of, well, the Fortnite logo is there as well. And also, the main thing would be the Fortnite logo. And this is where the issue comes into play. So the more accurate, the more complex your, function is to match whatever this is, the less likely it is that it's going to match other data outside of that real world. And this is where the paradox comes in. So, a more complex function can help your machine learning algorithm fit the training data, but it might result in an overcorrection that will fail the testing data. So, in a way, we can, this is, to the people who are perceptive, this is not a good thing. We want accurate training data, but also a match between our training data and testing data. Because the whole point of an AI, of a machine learning algorithm, is to realize that, hey, you are supposed to make a guess. You don't know. You know, the whole point about these algorithms is that they're supposed to make a guess, right? What the fuck's the point of these things existing if we tell them what they're supposed to think? There's the ones that the point of AI is to think instead of us. If we do the thinking first by giving it the testing data, then it's totally pointless. Yeah, and stuff like that. So the question is, what can we do to make it so that we can fit in certain traits of this to like better match this training data, but also be flexible enough for outside stuff like this right here? Well, this is where we go into like a more billion, a gadoinkillion, a bormillion ways of doing that, and I don't want to talk about any of them, except for one. It's called neural networks. So back to the Fortnite backpack example right here, right? So there's the whole point, the idea of a neural network focuses on aspects where we have to make multiple judgment calls in order to actually establish these things. So let's erase the Fortnite text across with that, right? We can see that these people are doing stuff like poses and stuff like that, and we also have the Fortnite silhouette stuff right there. But while the silhouette can be kinda easy to identify, how do I identify people, right? How do we identify that these are actually the silhouettes of like actually people, right? So it actually needs to be a couple of steps, and this is where neural network takes their play. A neural network, how do we identify people and poses though? Neural networks work as a way of layering your machine learning decisions. So for this instance right here, right? So we have to first identify that these things are people, and then we have to identify that what they're doing is like a certain pose of a certain like dance form, right? And we could probably save those. We can probably have like certain attributes of a human, right? So let's say like the small head, or like the limbs and like the general structure, right? Does it go like can we identify like limbs and stuff like that are connected to like the top area? So you have like the head, which is more circular, and then we have the limbs, which are connected to like the what's it called, top part. You know, what if the limbs were on the fucking legs, right? That's a good thing, right? And you might be saying, oh, Bowas, how do you know what's the top part? How do you know what the legs? That's another fucking layer of the perception. So that's another layer that we have to account for as well. So, in a way, neural networks are sort of like compounding different like aspects of it, but it also manages to sort of solve these issues where if we have this understanding, and this is still, and at the end of the day, we'd still be weighting these things, right? If we go back to the fucking, let's say the fucking llama, right? This thing right here, what do we have in common? Well, we can say that stuff like the saturated colors are stuff that's in common as well. And this is where having like a training set that like takes up multiple like variations of it is pretty important as well. Anyways, yeah, so the question that some people might be like, oh, Bowas, how do you evaluate, how do you evaluate these things, right? How can you verify that these things are true if you don't have all these multi-layered things, right? That doesn't make sense. Well, this is where the concept of forward and backward progression goes. So what you would normally do is you would have your training data, right? You would keep, after you're done with your training data, you get like a general idea of like what a person is, right? You would then you would also get like what those saturated colors are. It's at this point you would just get what a person is, right? Then you go forward in time and you would say, okay, now that we know like whether or not this guy's a person or not, can we identify whether this person is doing a dance move or something like that, right? And then once you say, okay, we have the identification of both a dance move, which is supported by the identification of a person, right? And then we can compare stuff like the saturated colors and stuff like that, and whether or not the person's doing a dance move, and that makes our ultimate result be this end game judgment right there. And suppose that we get it wrong. Okay, then we have to go backwards to see, okay, we have to change both the saturation and also we have to change maybe the saturation settings or the person settings as well, depending on the result that we got right there.
And then we would have to go backwards again to change our definitions of what a person is if we have to make our changes to what that person is in the first place. So, what that is, and I'm just going to type that out right here. First, you go forward in the, progression to get an understanding, to get the actual training results, and then you go backwards to make alterations on the previous aspects. So it would first go identify if person, and then if person, identify if dance move, and then we can go into stuff like how do you do fucking split things? I don't know. And then we can do both silhouette of person, and also saturated colors, so we can see like the differences between those colors and stuff like that. So then if we do get it wrong, then we have to say, okay, let's go back and we change the saturation potentially based off the results, and then we say, okay, maybe this a silhouette of the person, maybe we could change the weights of that, right, based off of the situation. And if it is a person, then we identify if it's a dance move, or then we can change our definition for that dance move. And then if that doesn't work, then we go back to the identification of it's a person in the first place. Anyways, yeah, that's it. See ya.